Good morning, everybody. Can you hear me?
Yes, Prof.
Yes, Prof.
Yeah. Shuni, the slides should be on the website. I was informed that they were put up last night. So while we wait, do we have any questions from the past three classes, three lectures? Any questions? If not, we're good. I'll start shortly after 8 a.m. So, Alfaraj, just write to Karen Kirk. All of you who are on in section B, please write to Karen Kirk, and she tells me that the wait lists are cleared. So she needs to hear from you because I can only tell her to clear the wait list, and I have to believe her. So email her and CC me, and you'll get cleared if you have credits free and you have no conflicts. Okay, there are no slides. TAs, can you check why the slides are not up on the web? I had given out the slides last night, I believe. Oh, I had not. My mistake. Oh, yeah, I have. So, can you please notify the website folks to upload the slides? The slides should have been up. The in-person lectures will start on the 9th. But trust me, you get a lot more engagement from Zoom. All right, let me begin. So here is where we were at the end of last class. We saw that neural networks have to be trained to emulate whatever or compute whatever function they're trying to compute. But one big issue is that we don't have the entire function. So just give me a second. I've got to shut my window. It's very noisy here. It's crazy. We live in a rural area, so people don't drive cars, they drive tractors. And the tractors are really noisy. So you have tractors going up and down the street all the time, making terrible noises. Anyway, so we saw that neural networks have to be trained to compute the function that they're trying to compute. But we don't have the entire function. We only have samples from the function that we are trying to estimate or model. And so the samples consist of input-output pairs, example inputs, and the corresponding function values at these example inputs. And from the subset, we have to learn to model the function. And the way we do it, for any given setting of the network parameters, the network computes some function f. This can differ from the target value d. And so we define a divergence function, a divergence between the output of the network and the target value. And the loss, the term we define as the loss, is the average divergence over all of our training samples. And so once the x's and d's are given, the only way to modify this loss is by changing the w. And so the loss is just a function of the network parameters w. And so we estimate the network parameters to minimize this empirical estimate of the expected divergence between the function computed by the network and the actual function. So that's what this loss is. And the hope is that when you minimize this loss, you actually minimize the error between the output of the network and the true target function over the entire space. So this ends up being an instance of function minimization. This loss is a function of network parameters. And so when we try to minimize this loss, we are basically minimizing a function with respect to its argument. So this is an optimization problem. And so we'll quickly take a quick look at function optimization and an initial discussion of derivatives. Now, suppose I were to have a function of this kind. This is x, this is f of x. And at any location, this function has a derivative. So let me call this derivative alpha. Now, what do you understand by the term derivative? Can anybody tell me? What do you understand by the term derivative over here? Anyone? Slope, rate of change, slope, slope, slope. Okay, that's what you've been taught, right? But then in the strictest sense of the word, what you mean by the derivative is this. At this location x, suppose you were to take a small step delta x. So a very infinitesimal step delta x. That is going to take you to a new location. And that results in a change. I'll call this y equals f of x. This results in a change delta y in the function, right? And so the slope, this derivative here, is simply the multiplicative term with which you must multiply delta x to get delta y. This is how you define the derivative. There is no other definition for the derivative. This is the only true definition for the derivative. So when I speak of derivatives, the actual definition of a derivative is as follows. The derivative of a function at any point tells us how much a minute increment to the argument of the function will increment the value of the function for any function y equals f of x. This is a multiplier alpha. The derivative at any point is a multiplier alpha that multiplies delta x to give you the corresponding delta y. This is the only way to define the derivative. There is no other way to define the derivative. So, and this is based on the fact that for continuous functions at fine enough resolution, the function is locally linear. Now, in your college classes or high school, you might have often have used this notation dy over dx for derivatives. How many of you are familiar with this notation? I'm sure all of you are familiar with this notation, right? Yes or no? Okay. So given this definition, does this notation make sense? Given this definition, does this notation make sense? Yes or no? It does. What if I told you it doesn't make sense? Then what would your answer be? Okay, so let me tell you why it doesn't make sense. And for that, here, if I have a scalar function of a scalar argument, then in this case, the argument is scalar and the function value is also scalar, right? In that case, y is a scalar, x is a scalar, so this is a scalar, this is a scalar, and we all know how to divide by scalars, right? And so I could always write, in this case, alpha equals delta y over delta x. And in the limit, this simply becomes dy over dx. So when x and y are both scalars, this notation is just fine. Except you're better off representing it as f prime of x than this one, Why is this notation better? Anybody tell me? Why is this notation better? Anyone? Multivariate case. This notation is better because it's telling you that it changes with the location x. Whereas if I write something of this kind, that information is hidden, right? So this is a much better notation because it actually indicates that the derivative itself depends on x. The more generic notation doesn't do so. But this works for scalars. Suppose, and so for scalar functions of scalar arguments, it's easy. Let me just draw this plot, right? Suppose I have some function and I am computing the derivative at x, right? And so there's a corresponding y. Then if I say the derivative alpha is greater than 0, then if I increase x by a little bit, what will happen to y? Will it increase or decrease? It's going to increase, right? If alpha is less than 0, then if I increase x by a little bit, what will happen to y? Increase or decrease? Decrease. So you can see, right? Delta y equals alpha dx, delta x. So if alpha is positive, then increases in x will result in increasing y. If alpha is negative, increases in x will result in decreasing y. And so when you look at this figure over here, anywhere where the function is increasing, the derivative is going to be positive. Anywhere it's decreasing, it's going to be negative. And at these local maxima and minima, over here, if you look very, very closely at the function, then a small step doesn't change the value of the function at all if the step is small enough. And so at these locations, the derivative is 0. Now, what happens in the multivariate case? It turns out that in the multivariate case too, I can use exactly the same notation. Now, clearly, in the multivariate case, x is a vector. So I cannot write 1 over x. Can you divide by a vector? Is this a valid notation in the multivariate when x is a vector? It is not, right? So I cannot write 1 over x. I can also not write dy over dx. This does not make any sense. So what does make sense? This notation still makes sense. Delta y, the change in y, is the derivative times the corresponding change in x. This making sense over here to you guys? Over here? Okay. And so now suppose x is a vector of this kind. So x is, a vector x1 through xn, okay, or xt. Then what will delta x be? Delta x is a small increment in x. What will the shape of delta x be? What's it going to look like? The same, right? Delta x is also going to be delta x1 through delta xt, right? Now, y, in this case, is a scalar. It's just a height, right? What is delta y? Is delta y a scalar or what is it? If y is a scalar, what is delta y in this case? It's also going to be a scalar. Delta y is going to be the same as y, right? So delta y is a scalar. Delta x is a vector of this kind. Delta x1 to delta xn, xt. So what will alpha be for this whole thing to make sense? Delta x is a column vector. Delta y is a scalar. What is alpha going to be? Anyone? Alpha must be a row vector, right? Nothing else makes sense. The math doesn't work otherwise. And so alpha is going to be a row vector, right? And so so this means delta y is going to be alpha 1, delta x1 plus alpha 2, delta x2, and so on, all the way to alpha d delta xt. This is how it must be written. This is how it comes out, right? Now, in this case, something interesting happens. Now, when x is a vector, let's look at a two-dimensional case. This is x with components x1 and x2. So let's say the current location of x is out here. Is there a unique direction? Now, when x was a scalar, You could either move forward or backward. Those were the only two directions, right? Here, is there a unique direction in which x can be modified, or is it possible for delta x to be in any direction? Over here, when x is a vector. Delta x can be in any direction, right? And regardless of the direction, this equation must hold. And so, suppose I take delta x in a direction where only this first component changes and the rest of them do not change. So that all of the rest of them do not get perturbed. I should still get delta y equals alpha delta x, but that's only going to leave me with this one because all of these delta x's are 0, right? And so in this case, when your delta x is perturbed only along one coordinate, then the multiplicative term that multiplies that corresponding delta x is called the partial derivative of y with respect to that component. And so this vector alpha, it's a vector of partial derivatives where each one of these is a derivative with respect to partial derivative with respect to one of the coordinates of x. This making sense so far? All of you? Yes, okay. So alpha is a row vector, right? How many of you have heard of the term gradient? Have you heard of the term gradient? Okay, what is the gradient? So here's what it is. When I'm living in some space x, then there's a term called the gradient g, and g lives in the same space as x. It has the same dimensions, and if x is a column vector, g is also a column vector. It turns out that the gradient is simply the transpose of the derivative. And so if I were to write delta y, that's what the delta y is going to be gradient transpose, gradient at x transposed times delta x. The gradient is simply the transpose of the derivative. That's just terminology. That's because the gradient is in the same space as the original data. That making sense to everybody? Yes or no? Okay, so can I see a few thumbs ups, please? So far, I have never got more than 10 people agreeing with me. Okay. And so then, because this again is a function derivative of y with respect to x, I'm going to use this notation, this inverted triangle called nabla, subscript x, which means I'm taking the derivative of y with respect to x. This derivative is basically a vector of partial derivatives. And the gradient is simply the transpose of this guy. The gradient lives in the same space as x. So far, so good, right? So I can write it like so. I can say that the increment df of x is this increment here, it's a scalar, is a derivative vector times the x increment vector, right? This is what we've got. This is an inner product between two vectors. It's actually the inner product between the gradient. Anytime you speak of x dot y, that's simply, you're assuming that x and y live in the same space. If they're both column vectors, this is just x transpose y, right? You might be familiar with this notation. So, but doesn't matter. The point is, this is an inner product between two vectors. Is that making sense? The increment is an inner product between the derivative and the step. Are you good with this? Yes or no? Okay, so if you're good with that, now let me ask you this question. What do you think, how do we interpret this derivative? It's just a vector of partial derivatives, but what does it mean? Does anybody have an intuition for this? What does this vector of partial derivatives mean? So Preet, can you explain why this is the direction of steepest ascent? Why? So anybody else want to explain why this is the direction of steepest ascent? Why is that? You know the answer, but I'm asking you why.
Um, Professor, because you're essentially trying to like reach the global minimum. So this would essentially
No,
give us.
I'm not asking in terms of objectives. Why is this? You for the orthogonal? Are they orthogonal to the isotopic line? Is that it? Okay. So we agree that this is a vector inner product, right? Now, let me ask you this. If I give you the inner product between two vectors, x and y, what is this? You remember the formula for this? If the angle between the two vectors is theta, then what is the inner product? Anybody remember this? Anyone? Come on, we have
Mod x mod y cos theta.
mod x, mod y, cos theta, right? This is the inner product between the two vectors, right? And so if I look at this, if I have u transpose v, it's mod u mod v cos theta. So let's say this is v and the blue vector is u, right? Then as u keeps rotating around, when is this inner product maximum? Anyone? When is it maximum?
At 0.
When the two are perfectly aligned, right? Angle is 0. So when blue is right on top of the red. And when is it minimum?
Orthogonal.
Orthogonal? When is it minimum? When blue is exactly opposite to red. Look at this curve, right? Theta is 180 degrees. You see this? I'm plotting the inner product to the right. So when the blue sits on top of the red, it's peaking. And the blue is pointing in the exact opposite direction as the exact opposite. It's a negative of this value. It's the minimum. Everybody good with this so far? This little picture. Okay. I have one. All right. So let's see. Now df was the inner product between the derivative and dx, right? So this red line is your derivative. The derivative is fixed. The only thing you can change is the direction in which you take your step. Dx is the blue line, right? When is this inner product maximum? Anybody? When is this inner product maximum? Looking at the figure. Come on, guys. When the step that you take is exactly in the same direction as the gradient, right? So in other words, so in the space, if your gradient points in some direction, you could take steps in any direction, it doesn't matter. And this relation will still hold. But df is going to be maximum if you take the step in the same direction as the gradient. That making sense to everybody? Yes or no? Right? Can you give me some thumbs up? So because everything is going to be dependent on this, right? Okay. And so here's where we are. At any point, you have a gradient. The gradient is the vector of partial derivatives, but that gradient is the direction of steepest ascent. If you take a step in that direction, that's when the function is going to increase fastest. Now, if you want the function to decrease, which direction would you take the step in? From here. Anyone? The exact opposite, right? Moving exactly opposite is going to decrease the function fastest. And so, wait. Vanjari, I don't understand your question. What do you mean by rule
We are
out the
taking
vector product
inner
between
products,
gradient?
right? You
Pardon
said
me?
we are taking inner products, right? Between derivative and gradient. So
Yeah,
why did
what
we
is the
rule out
vector product? That's an outer product. That's going to give you a matrix,
Okay.
right? So whereas you want a scalar. The scalar is going to be an inner product, right?
Right.
So, okay. And at these points, the minima or the maximum, that's where a small step doesn't change the direction at all, change the function at all. At those points, the gradient is going to be 0. There's no direction in which you can walk, where the function is going to either increase here or decrease over here. And so there's another rule. If I slice the function at some height, then I'm going to get an edge. That edge is called a level set. And the corresponding value of the function is the level curve. And there's a property which says that the gradient is always orthogonal to the level curve. That's something that we will use, but I'm not going to explain why. Now, there's also another property called the Hessian, which is the matrix of second derivatives. Again, the function, it's a scalar function of many variables. And so this matrix of second derivatives where the ijth term is the derivative of the function with respect to xi and xj. This is called the Hessian. We'll encounter the Hessian again later. So here is our first pole. And let me release the pole. Can you see the pole? Okay, 5 seconds. Okay, some of you are unable to see the pole, but let me share the pole, right? And so here is what all of you thought over here. But before we continue, first question, which are the three true statements? Anyone? Which are the true statements in the first question? You guys want to reply? 1 and 2. At any x, there may be many directions in which we can step, such that f increases. The direction of the gradient is the direction of the steepest increase, right? And is the gradient the derivative with respect to x? Why is the third statement not true? It's the transpose of the derivative, correct? If f of x is an n cross 1 column, is a scalar function of an n cross 1 column vector, what is the shape of the derivative with respect to x? What is the shape of the derivative? 1 cross n, right? And Daisy, we are not guaranteed that x will increase. At maxima, it's not going to increase anymore. It's just that that if x increases, that's the direction of steepest increase. If it's a smooth function, it will increase in some directions and decrease in others. It's only at maxima and minima that it won't. At maxima in particular, that there's no further increase, and so the gradient is going to be 0. So now here's the problem of optimization. Going back to our problem, right? You're given a function of this kind, like loss of w, and we want to find the value of the argument where the function is minimum. It can be pretty ugly, right? So functions can have global minima, they can have global maxima, local minima, inflection points. We want to find the location of the global minimum. Now, we've seen how to do this in school. If I have a continuous function of this kind, and it's a function of a single variable x, then you all know how you did this. You just found the place where the derivative was 0. So you equated dy over dx to 0. You solved for x. And was that sufficient? Was that sufficient to check for where the derivative was 0? Okay. So to get back to we'll get to this. A minimum is a turning point. Why is it a turning point? The function is decreasing till it hits the minimum, but then it turns and begins to increase. We find a turning point, but it's not sufficient to find a turning point. You have other criteria to consider. And let's see how many of you are familiar with this other criterion. Why is this? Why am I not able to? Okay. What's going on? Okay. I assume you can see the poll. I'm giving you only 30 seconds for this one. Some issue, those if you're logged in through Andrew, you should be able to see the poll. I'm not sure why you're not able to see it. Okay, 10 seconds. All right, let me end the poll, right? So here's what all of you thought. And okay, which statements are true? Anybody? Which are the true statements here? 3, right? Which of the following criteria would be true? The third one. The derivative must be 0, the second derivative must be positive, right? This is the one. So here's what it is. If you have a function of a single variable, when the function is increasing, then any increment in delta x is going to result in an increase in y. So the slope will be positive. When the function is decreasing, the slope will be negative. And so the but at both maxima and minima, the derivative is going to be 0. So it's not sufficient to look at the maxima and the minima. In fact, if you look at the derivative, then in this region, while you're arriving at the maximum, the slope is always positive. So the slope is going to be positive. When you're going away from the maximum, the slope is always negative. So the slope goes from being positive to being negative and hits 0 at the maximum. At the minimum, you have the exact opposite criteria condition. Before you hit the minimum, the slope is negative. So, this thing is below the horizontal line. And then once you go past the minimum, the slope becomes positive. So the slope goes from being minimum, negative, this is the 0 line, to being positive, and the slope is 0 at the minimum. Both at maxima and minima, the slope is 0, right? But there's something else that's indicative of the derivative, of whether it's a maximum or a minimum. At a maximum, the slope goes from being positive to being negative. So the slope of the red curve is going to be negative. The slope of the slope is going to be negative at the maxima. At the minima, the slope goes from being negative to positive. So the slope of the slope is going to be positive at these places. And so, as we learned in school, we look at the second derivative, the slope of the slope. And at maxima, the slope of the slope is going to be negative. The second derivative will be negative. At minima, the second derivative will be positive. And so in school, when we actually tried to find a minimum of a function, we found where it was 0 and where the second derivative was positive. This making sense to everybody? You must remember all this, right? Is this making sense? Okay. And so here's what we did, right? Find the value of x at which f prime x is 0. That's always going to be a turning point, or almost always. We'll see where it's not. And then check the second derivative. If it's positive, x is a minimum. If it's negative, it's a maximum. Easy. But then you can have other ugly things. For example, if you have a function of this kind, it has a minimum, maximum, it has an inflection point, it has a minimum. So all of these are critical points, points where the derivative is 0. They're called critical points. Not all critical points are turning points. Only maxima and minima are turning points. That's where the function turns. If you plot the derivative is going to be 0 here, it's going to be 0 here, and it's going to be 0 here. But then here's the derivative curve. At the maximum, the derivative goes from being positive to negative. At an inflection point, at this inflection point, the derivative is always negative. It's just that its magnitude reduces and then increases again. So it goes from being negative and goes back to being negative. And then at the minimum, the derivative goes from being negative to positive. But then at inflection points and at maxima and minima, the derivative is going to be 0. And so if you look at the second derivative, then you find that the second derivative is going to be negative at maxima, positive at minima, and at these inflection points, more often than not, it will be 0. That's basically, this red curve is the derivative of the blue curve. So these are the tests we can run, right? But then when we get to more variables, it gets more complex. So let's look at what happens with functions of multiple variables. So you're going to have a function of this kind. The minimum is still going to be a turning point, but it's turning in multiple directions. Over here, a turning point was because as you approached it, the function went from being increasing to being decreasing, and there was only one direction to travel. Here, and I mean, there were two directions. You could go from left to right or right to left. Regardless of which way you went, the function would initially be increasing and then decrease. So it's a turning point. Here, there are infinite different directions in which you can travel. You could be coming this way, you could be coming this way, you could be coming this way. And regardless of which direction you approach this point from, initially the function will be decreasing and then it will be increasing. It's going to be a turning point from every direction, and it's going to be a minimum from every direction. So, and at the minimum itself, regardless of the direction you arrive from, the slope is going to be 0. That makes sense for the multivariate case, right? And so the optimum is still a turning point. The gradient will be 0, and we have to find the location where the gradient is 0. So how can we do this? It turns out the equivalent of the second derivative in the multivariate case is the Hessian. And so we would write out the formula for the derivative or the gradient and equate it to 0. That would give us some potential solutions for x. And then at that x, you can compute the Hessian matrix. And the Hessian matrix is going to be positive definite, meaning all the eigenvalues are going to be positive at local minima. All the eigenvalues of the Hessian are going to be negative at local maxima. And then you can get other things like saddle points. So for example, if you have a function of this kind, which looks like a saddle, right? Then, so this is a function which is a saddle. So if you approach in this direction, this is a minimum. If you approach in this direction, this is a maximum. So in this case, the Hessian will have two eigenvalues. One of them will be this, the second derivative along this direction. The other is the second derivative along this direction. And you will find that one of the eigenvalues is going to be negative, and the other eigenvalue will be positive. It's only at strict minima that all the eigenvalues will be negative. And so you'd run the test and you can find the solution for x. But, and there's a little example on the slides where we actually solve for this for a toy problem. The problem is that, for most functions, you cannot simply solve for the minimum. You can't write out the derivative and get a nice closed form solution for x where the derivative is 0. In these cases, we need iterative solution. So what we do is we begin with a guess. You have this ugly function and you say, I think the minimum is over here. Then you look at that, go to that point, you look around, you find it's not a minimum. How would you find that it's not a minimum over there? What is your check? How do you find that it's not a minimum? Anyone? Check the derivative, right? And if the derivative is not 0, then it's probably not a minimum. So then you take a step. And then you come to a new point. And then you check again, am I at a minimum? If I'm not, I take another step. And I keep doing this until I get to a point where the derivative is 0. This would be the same for the univariate case or the multivariate case. Start with an initial guess. Check if it's a minimum. If not, take a step. Keep doing this till you arrive at the minimum. There are a couple of questions. Which direction should I take a step in when I do this? Should I be going this way, or this way? And how big must the step be? These are the two questions, right? So let's look at this for a simple toy problem, okay? Scalar. Now let's say this function y is what you're trying to minimize. And so you're at some initial value x0, okay? And then at this point, you have some value y0, you check around, and then you find that the derivative is positive. So if it's positive, then will going forward increase y or decrease y? What will happen? Over here, if I increment x, will y increase or decrease? It will increase if the derivative is positive. So which direction should the step be in? Should I be going forward or backward? Remember, I want to minimize y. Which direction should I take a step in? I should go backwards, right? So I'm going to say x1. The next iteration is going to be x0 minus some step, right? So I come here. I get to x1. But then at x1, I have some other value of y. And I check the derivative over here. And I find that the derivative is negative. Okay. If the derivative is negative, then if I increment x, will y decrease or increase? What will happen if the derivative is negative? What do you guys think, right? Decrease, right? So over here, it means the function has this direction. So should I increase x or decrease x? Increase x, right? Because going forward is going to decrease the function. And so now my next step is going to be x2 equals x1 plus eta. Very simple procedure. At each point, you find out, look at the derivative and determine whether increasing x will increase y or decrease y, and you take an appropriate action. So this is what it's going to be. You initialize x0, you check the sign of your derivative. If it's positive, you take a step back. If it's positive, going forward will increase the function. So you take a step back. If the derivative is negative, then it means that increasing x will decrease the function, so you take a step forward. So if the sign of the derivative is positive, xk plus 1 is xk minus step. If it's negative, xk plus 1 is xk plus step. Is this making sense to everybody? Yes or no? Very easy, right? And so, but instead of writing it in this manner, can you think of a nice short way of just writing this exact same equation? How else could I write it? Anybody? I could just write xk plus 1 equals xk minus sine of derivative times step, correct? And you can verify that this satisfies both. When the derivative is positive, you end up with this guy. When the derivative is negative, you end up with this guy. This making sense to everybody? Right. And so I can compact both and just write it like so. If xk, I can say xk plus 1 equals xk minus sine of the derivative times step. That still leaves us with this issue of how big the step must be, right? And so suppose you have a function of this kind. And this is the ideal kind of function. This is how we like functions to be. So this is the minimum, right? If you are out here, do you want to take a big step or a small step? Big. You want to go here. If you're out here, do you want to take a big step or a small step? Small step. What is the distinction between these two guys? It's the magnitude of the derivative, right? When the magnitude of the derivative is large, you want to take a big step. When the magnitude of the derivative is small, you want to take small, careful steps. So let's factor that in. And if I factor that in, instead of just writing sine times step, I can say some step size times the derivative itself. This actually factors in both the magnitude of this derivative and the sign of the derivative. And so this is the actual update rule that you're going to use. Does this make sense? Okay, everybody? Yes, no? I'd like to see a few thumbs ups. I have like 4 or 5. Maybe you can give me 20. All right. Okay, so here is your third poll. And I'm assuming you can see the poll. 20 seconds, guys. Is it the same poll? It shouldn't be. I guess it is. Doesn't matter. Let's see how many gig if you get it right the second time around. Okay. Let me stop. This seems to be a mistake. Not really. Stop sharing. Okay, so here's where you are. We are right. At any x, there may be many directions in which we can step. The direction of the gradient is the direction in which the function increases fastest. And the third one is wrong. You all agree, right? So based on this, when I get to a multivariate function, the gradient is the direction in which the function increases fastest. So if this is your initial estimate for x, which direction do you want to move in? Which direction do you want to move in? If this is you want to go backwards. So you want to always take a step in the negative of the gradient. So to find a maximum, you move in the direction of the gradient. To find a minimum, you move exactly opposite the sign of the direction of the gradient. Xk plus 1 equals xk minus some scaling term times the gradient. The scaling term is something, there are many solutions to choosing it. We'll see some of those later, okay? So that's what we will do. We start off at some point, take a step against the gradient, keep doing this. When do we stop? We can stop when the derivative is 0, right? Or we can stop when the additional steps don't change the function very much. So of these two, which would you think is the more reasonable criterion? Anyone? Which is the more reasonable criterion? It turns out the first one is, and we'll see why, okay? And so here's the gradient descent algorithm. You're going to initialize x. Then you keep taking steps against the gradient until the steps don't change the function very much, okay? Now, there's gradient descent algorithm. It's a gradient descent algorithm because you're always taking a step against the gradient. You're descending the gradient. So it's the gradient descent algorithm. And for functions like these, it will behave very nicely with nice bowl-shaped functions. You know, when you're far away from the minimum, you'll take large steps. You'll be more careful near the minimum, and eventually you'll get there. If you have crazy functions like these, you can arrive at local minima, global minima. You can arrive at inflection points. You don't really have any control, but you have no choice. This is the approach we will generally take. So this poll should not be deja vu, but let's see, maybe it is. Okay, 20 seconds. Five. I'll end this here. Here's what you guys thought. Stop sharing, go back. Okay. Which of these statements is true? In which direction must we move to achieve the maximum decrease in f? Exactly opposite to the direction of the gradient, right? It's perfect. This is the good one. So here's our original problem. We've figured out what it means to what derivatives are and how we can use those to minimize the function. So now we are given a training set of input-output pairs. We defined a loss, which is a function of only the network parameters. And we want to minimize this loss. This is a problem of function minimization. So we can use gradient descent. You'd initialize your network parameters. And then at each point, you modify the current estimate by taking a step against the gradient of the loss with respect to the network parameters. And you'd keep doing this until the loss no longer decreases. Easy enough, right? So we've sort of set up the problem. Let's define all the terms. Now, here, this is our problem setup. Given a bunch of training input-output pairs, we want to minimize this loss function. But for this to be solvable, what are all the things we must define? Can somebody tell me what are the things that are not being defined properly? What must we define? Anyone? We want to define what are these input-output pairs. I mean, what is a compute? What is an image numerically? What is the target? We have to define these input-output pairs, right? Everything must be numbers. We have to define the function f. What is this function f? And then we have to define the divergence. These are all the things we must define. Otherwise, this whole thing is not solvable. Everything must be numeric, right? So let's start off with defining this function f. For us, the function f is a multi-layer perceptron. And unless I state otherwise, it's a directed network where all the edges point in only one direction. And so this is a network without loops where the neurons are connected in layers. Data inputs go into the input layer, and you're going to read the output from the output layer. So we will assume a layered network. Each layer of neurons gets inputs only from the earlier layers and output signals only to the later layers. So this layer over here would get information from these layers and pass its outputs would go to these layers. I'm going to refer to the inputs, although there are no units over here, as the input layer. I'm going to refer to the output units as the output layer, and everything in between is a hidden layer. Standard terminology. These hidden layers are not really hidden. It's just that their individual outputs are not of interest to us. We are interested in the final output, like in the XOR. What are the individual units of this network? We're going to assume that the individual units are perceptrons, which have the structure we saw before. Each perceptron has a bunch of inputs. We first compute an affine function of these inputs, weighted sum plus bias, which I represent by z typically. And then we put this affine term z through an activation function f. This is the structure that we are going to assume. More generally, a perceptron is any differentiable function of its inputs and its parameters. Now, I'm going to assume this guy, unless otherwise specified, and the parameters of this perceptron are the weights and the bias, right? Now, the other thing is the activation function. What is the activation function? So there are different kinds of activation functions. The earliest one that people used was the sigmoid, which is, remember the activation function gets the input z. So the sigmoid is 1 over 1 plus e raised to minus z. Now, if z is a large negative number, you can see that, negative times negative is positive. Okay, tell me this. If z is a large negative number, what is e raised to minus z? Is it a large negative number or what is it? If z is a large negative number, over here. If z is a large negative number, z is minus infinity, right? Minus of minus infinity is going to be plus infinity, right? E raised to infinity is infinity itself. So this term becomes infinite. This whole term becomes 0. Does that make sense? When z is a large negative number. So out here, the function is going to be 0. If z is a large positive number, then e raised to minus z becomes 0. So this term goes away, and this whole function becomes 1. Out here, the entire function is going to be 1. And so the function goes smoothly from 0 to 1. What will the derivative look like? The derivative is initially 0, right? And then at this point, the derivative begins to increase, and it's going to increase to some value. And it's always positive. Then the derivative begins to decrease. And then the derivative goes back to 0. So the derivative of this function has this shape. In fact, it has this formula. And you can see it's symmetric. When for large z and for large negative z and large positive z, it's going to be 0, and in between it's going to peak. So this is your sigmoid activation. There's the other activation, which is the tan H, which has the same structure, but the whole thing is shifted and scaled. So it's centered at 0. Instead of going from -1 to 0 to 1, it goes from -1 to 1. And its derivative is also going to have this bell shape. Then you have the rectification function, the so-called ReLU. It's 0 for negative numbers and 1 for positive numbers. What will its derivative look like? What will this red curve's derivative look like? Anybody? What does its derivative look like? Anyone? It's going to be 0 when the input is negative. It's going to be 1 when the input is positive. And at 0, it's kind of undefined, but if you wanted to plot it, it would be a step. And the soft plus is a smooth version of this guy, the blue curve, and so the derivative is actually going to look like a sigmoid. Oh my God. A sigmoid is really badly drawn. Okay, you get the idea. So these are all the different activations we can use. You can also have vector activations, where I just say that instead of the activation taking a single scalar and producing a single scalar, it can take a set of numbers and produce a set of numbers. So the function operates on a set of inputs to produce a set of outputs. What this means is that if I modify any single input over here, all the outputs are likely to change. Whereas in something like this, if I modify the input, only the corresponding output changes. So let's look at an example of this one, the so-called softmax. So the softmax is this guy here, where it takes a bunch of inputs, but then each input is exponentiated. But then all of the exponentiated inputs are normalized so that they sum to 1. That way, all of these outputs, these y's, if you sum them, that sum is going to be 1. So suppose I increase z1. What will happen to this guy in this case? Will it increase or decrease? Each z is being exponentiated. So if I increase z1, what will happen to this guy? Is it going to increase or decrease? How many of you think it's going to increase? Give me a thumbs up. Okay. What about this guy? Is this going to increase or decrease? If I increase z1, is this going to increase or decrease? It's going to decrease, right? So the derivative of y1 with respect to z1 is going to be positive. The derivative of yl with respect to zl is going to be negative. So changing one z changes all the y's. So this is what I call a vector activation, where you take in a vector of inputs and produce a vector of outputs, where changing any one component can change all of them. Right? This making sense to everybody? I'd like to see a few yeses. Okay.
Sir, is J the number of inputs?
So where is J? J is the sum. You're summing over all of the inputs over here, right? In this case, for Y, you're summing over all of these guys. And this is just telling you how the individual Z's were computed, okay? So what this means is that if I change this parameter here, all of the Y's will change, because it will change this Z, and that's changing this Z will change all of these Y's. Now, even when each of the neurons is individually computed, I can still think of this entire set, this entire layer, as a vector activation, where the interaction between a single input and the remaining outputs is 0. You can view it as a single vector activation. So we've defined the function f. It's a network. Its parameters are it's an MLP. Its parameters are the weights and biases of the perceptrons. And the activations can be vector activations or scalar activations, right? Is the distinction between vector and scalar activations clear to you guys? Yes, no. Right. In the scalar activation, changing the input, one input changes one output. In a vector activation, it can change all of them, right? The next thing is, what are these input-output pairs? So for these input-output pairs, these are the inputs and the outputs. You're given a collection of training data, x1, d1, x2, d2, and so on. Each input is actually a vector. Now, corresponding to each input, there's a target output. This is what you want the network's output to be. And D doesn't have to be scalar. D can also be a vector. And then at each input, you have a network, and the number of outputs that the network will have must be the same as the number of components in the desired output. So for each input, there's an actual output of the network, there's a desired output of the network, and there must be this, and the number of components should be the same in both of them. This making sense? The distinction between D and Y? Yes or no, guys? I'd like to see it, at least a dozen yeses, so I know I got 10% of the class. Okay, Delphine. Where did I lose you, Delphine?
You lost me in this slide, the vector notation slide.
Here, you have X, which is going to be some vector, right? D is the desired output. It's the function value that you want it to be. So you might say that for each input, the network produces a vector of 4 outputs. That making sense?
Yeah.
Okay. So this is the desired output. Then if the desired output has 4 components, how many outputs must the network have?
The same.
The same, right? And so there are 2 distinct terms over here. The first is the desired output for each input and the actual output for each input. And these 2 will have the same number of components. That makes sense?
Yes, it does. Thanks.
Okay. So what about the input? The input is a vector of numbers. So, or it could even be a scalar if the input size is 1, right? So for example, it could be a vector of pixel values, or it could be a vector of speech features if you are working on speech signals. Or if you're working on text, now text is obviously not numeric, so we will somehow have to derive a real valued vector to represent the text. We'll see how later in the course, but eventually this thing has to be a vector of numbers. Now, what about the desired output? The desired output can be real valued, or a continuous number, or it can be a classification output, right? So if the desired output is a real value, like a regression, it can be anything. Then you have no special tricks required. Typically, we don't even use an activation function. You're just going to add up the outputs of the computer weighted sum of the outputs of the penultimate layer. And if the desired output is a scalar, then you're just going to get the network will have a single output, which is a scalar. If the desired output is a vector, the network is going to have many outputs, which is a vector. Basically, it's just a network. And when you're trying to predict real valued numbers, then nothing magical. You don't even need an activation function. You just compute a weighted sum, the affine function of the outputs of the penultimate layer. Okay. But then if you're trying to perform classification, then the desired output is going to be categorical. If the desired output is binary, like, you're doing binary classification. Is this a cat or is this not a cat? Then the desired output is going to be, it's actually going to be simple, right? If it is a cat, the desired output is 1. If it is not a cat, the desired output is 0. So which means that you only need a single, there's a single scalar output, which has to switch between these 2 values. So the network will just have a single output neuron. And in reality, although the desired output is going to be switching between 1 and 0, what we will use is a sigmoid activation, which slides between 0 and 1 for this output neuron. And the output of the sigmoid can be viewed as the probability of class 1 given the input. So this goes, just to give you an idea, if these are all the features of the cat, right? Then out here, you're very certain that it's not a cat. Out here, you're very certain that it's a cat. In between, you become increasingly, you're not too sure, but you become increasingly certain that it's a cat as you go from here to here. So this is what your activation function is going to look like, right? And you can think of this as the probability of cat. So when you have a binary target output, you will use a network with a single neuron output, and its activation will be a segment. Now, if you have is this making sense? Yes or no? Okay. Now, if you have a multi-class output, for example, if you're trying to classify between 5 classes, cat, dog, camel, hat, and flower, these are not numbers. How do you convert them to numbers? So what we will do is arrange them in some canonical order: cat followed by dog, followed by camel, followed by hat, followed by flower. There are 5 possible classes, so there are 5 elements here. And now our numeric representation of the output is going to be a 5-component vector, where the component corresponding to the actual desired output is going to be 1, and all the rest are 0. So for example, if you provide an image classifier with an image of a cat, then the cat component, which is the first one, will be 1, the rest will be 0. If the desired output is dog, then the dog component will be 1 and the rest will be 0. And if it's a camel, the camel component will be 1 and the rest will be 0. So these are what are called one-hot vectors. Only one element is hot and it's 1. The rest of them are 0. And the element that's hot is the element corresponding to the class that it represents in this canonical ordering. This making sense? Yes or no? And this one-hot representation, okay? And so in this case, if I have n classes, the network must clearly have n outputs. So if I have, for example, this cat, dog, camel class, I'll have one output corresponding to cat, one output corresponding to dog, right? One output corresponding to camel. And all of these are going to be values which go in between 0 and 1. And the network is designed so that all of these outputs together sum to 1. Which activation would I use if I want the outputs to sum to 1? Anyone? Which activation would I use? I'm going to use the softmax, right? And so now, suppose I provide an input of a cat, right? An input image of a cat. What do you want the output to be? Ideally, you want the cat output to be 1, and you want all the rest to be 0, right? On the other hand, if I provide an output, a picture of a dog, what do you want the output to be? It's going to be 0 here, 1 here, and the rest must be 0, right? So that's how you want the target to be, right? And so we will actually use a softmax activation, because we know the softmax activation produces probabilities which sum to 1. And the ideal thing is that if it's provided an image of a specific input of a specific class, say an image of a cat, then you want it to compute a probability of 1 for cat and 0 for everything else, although in reality it would be something not quite so perfect. So in a typical setting, you'd be given a number of data instances, e.g. images of digits, along with information about which digit the image represents. In binary classification, based on these, you'll be trying to perform a classification such as, is this an instance of 2 or not? In multi-class classification, you'd say, which digit is this, right? And so for the binary classification case, only the instances that are 2 will have an target output of 1. The rest of them will have a target output of 0. And you'd have a single neuron in the output with a sigmoid activation. In the multi-class classification case, each of the corresponding to each image would be the actual label for the class, except this is going to be represented in what format? How will this be represented for the multi-class classification case? Anybody? We just went through this. It's going to be a one-hot vector, right? Each of these is a different one-hot vector. And the network itself will have as many outputs as classes, right? And so we've defined the function. We've defined the input-output pairs. The last thing to define is the divergence. What is the divergence? Now the divergence is a very interesting function. This divergence it has this property. It has a function, or it's always a function of two variables, x and y. And this will be 0 if x equals y. And it's going to be positive if x not equal to y. Basically, it says that when x is not equal to y, then there's a distance between the two, and the distance can only be positive. When x is equal to y, the distance between the two is 0, right? So for this loss to be differentiable, this divergence function must be differentiable. If the divergence is not differentiable, the loss is not differentiable, and we cannot apply gradient descent. And now, what kinds of divergences can we use? If you're doing real valued predictions, for example, if you're doing if you're doing some kind of a regression and you're predicting real valued vectors, then an obvious divergence function is simply going to be the squared Euclidean distance, which is going to be half. This term half is for convenience. We always have the half, and it's going to be y minus d, or the squared norm of y minus d, which is to say it's a component-wise sum of the square of the difference between the actual output and the desired output. And now when you take the derivative of this divergence with respect to the output of the network, with respect to y's, you'll see why you have this half. When you take the derivative, the 2 comes out and cancels this half. And the only thing that you're left with is y minus d. Now, we know that y minus d whole squared is the same as d minus y whole squared, right? So when I take the derivative, why is it y minus d and not d minus y? Then you can think of it in terms of math. You can say, okay, this is actually there's a minus y over here, so there's a minus that comes out. You can get your head twisted. But there's a very simple way of thinking about it. Suppose this is my desired output, right? And suppose my actual output is y, is below it. Then is y minus d going to be positive or negative in this case? If the desired output is going to be negative. Do I want to be increasing or decreasing y to reduce the error? In other words, if this guy is below this d, then increasing y is going to decrease the divergence, correct? So if y minus d is negative, then increasing y will decrease the divergence. That's basically what this is telling me, right? This is when this guy is negative, increasing y will decrease the divergence. If y minus d is positive, will increasing y, increase or decrease the divergence? If y minus d is positive, what will happen? It's going to increase. And so you can take a look at this derivative over here. You can see that if y is greater than d, this gives you a positive slope. Increasing y is going to increase the divergence, correct? If this is positive, then if the derivative is positive of the divergence with respect to y is positive, increasing y is going to increase the divergence, correct? Yes or no? And so you can see this. If y is greater than d, then increasing y is going to, then y minus d is positive, increasing y will increase the divergence. So it has to be y minus d, right? It cannot be d minus y. If you had d minus y, and if y is greater than d, this is going to be negative. And if this is negative, then the information it's telling us is that increasing y will decrease divergence, which is not true. So the only way this works is if y is y minus d and not d minus y. You can sort of think about it in terms of the sign of the derivative. But anyway, let me move on, right? For the binary classification, we have another issue. So let's say I have only two classes, right? 1 and 0. Suppose the target output is 1, but the network output is 0. So your the image is that of a cat, but the network is 100% certain that it's not a cat. Is it just slightly wrong or infinitely wrong? If the target output is 1 and the, okay. So also if the target output is not a cat, but the network is absolutely certain that it's a cat, then is it just slightly wrong or infinitely wrong? And so you want a loss which goes to infinity when the network is certain of the wrong thing. That's what the scale divergence is. It's minus d log y, 1 minus d, 1 minus log 1 minus y. So if d is 1 and if y is 0, then log of 0 is minus infinity. You're going to get infinite error, right? This will become 0. If y is 0, log of 1 becomes 0. So this term disappears when d is 1. And so you're going to be, if the network is infinitely wrong, if d is 1 and y is 0, this becomes infinite. If d is 1 and y is 1, this becomes 0, right? So on the other hand, if d is 0, then 1 minus d is 1, right? And now if y is 1, you end up with a log of 0 again. And so again, this becomes infinite. The only time, so anytime this thing has the property that makes sense to you guys. No? Okay, let's just see this. Let's consider the case d equals 1, right? So if I say minus d log of y, you can see that if y is also equal to 1, this becomes 0. So this becomes 0, correct? Yes or no? If d and y are both 1. But if d is 1 and y is 0, what is log of y? What is log of 0? Minus infinity, correct? And so I put a minus over here and this becomes plus infinity. So you can see how this satisfies our requirement. When both are the same, this is 0. When the network is absolutely certain of the wrong thing, it's infinite. Make sense? Same thing over here, right? This is the other side. If d is 0, then 1 minus d is 1. Log of 1 minus y. If d is 0 and y is 1, this becomes log of 0. And this becomes, if I put a minus out here, this becomes infinite. Whereas if d is 0 and y is also 0, it becomes 0. And so this is how this works. That it actually penalizes you infinitely for being infinitely wrong. Now, this has an interesting characteristic. If you look at the derivative, the derivative is this minus 1 over y and minus 1 over 1 minus y. So here's the thing. I could have very well used the Euclidean distance between y and d. The Euclidean distance is the red curve. But the Euclidean distance doesn't penalize me infinitely for being completely wrong. Whereas the KL divergence penalizes me infinitely for being completely wrong. It's going to be 0 when you're perfectly right and infinite when you're perfectly wrong, regardless of whether d is 0 or d is 1, right? But then observe something. The slope of the KL divergence is not 0 at the minimum. Do you see this? This slope is not 0. Can you see this over here? And in fact, if you look at it, here's what it is, right? If d is 1, then you want to push y towards 1, right? And so if d is 1, you want to keep increasing y. And increasing y must decrease the error. So you get minus 1 over y. You can see that this term is always positive. And so the slope is always negative. On the other hand, if d is 0, you want to decrease y. So you want the slope to always be positive, right? Because you're taking a step against the derivative. And so you get 1 over 1 minus y. But more importantly, the derivative is non-zero at the minimum, which is why you can't just use, you can't just use a derivative check for 0 when you're doing gradient descent. You have to check the actual function value, okay? Now, same thing for multi-class classification. You have the same thing, except now you have the KL divergence is minus summation d log d over y. What is this? D is the desired output. The desired output is always going to be either 0 or 1, right? And so I can write this out as summation d log d minus summation d log 1. Now d is either going to be 0 or 1. When d is 0, this term becomes 0, and so this whole thing becomes 0. When d is 1, this term becomes 1, so log of d becomes 0, so this whole thing becomes 0. So regardless of, in every case, this first term becomes 0. This disappears. Because either, if I have a one hot vector, then the components are either 0 or 1. So if it's 0, this term becomes 0. If it's 1, this term becomes 0. Either way, this gets cancelled out. So you're only left with this term. Now, in this term, d is going to be 0 for all the non-target classes, and it's going to be 1 only for the target class. So basically, you're just left with minus log of the probability assigned to the target class when you do a KL divergence in the multi-class case. This makes sense to everybody? Did this make sense? Right. And then once again, you can see that if I take the derivative of this loss, the loss is only a function of the probability assigned to the true class, right? And so if you look at the derivative, does this have a derivative with respect to the probabilities assigned to the other classes? Yes or no? It does not, right? This is just a function of the probability assigned to the true class. And so all the other terms will become 0. And for the true class, the derivative is going to be minus 1 over the probability of the class. I'm going to go over a couple of minutes, guys, right? And once again, when you get the correct answer, you can see that the slope is actually 1, right? If you get the ideal answer for the correct class, y will be 1, and the slope is actually going to be minus 1, right? And so, again, the slope is, this slope doesn't become 0 at the optimum. And so when you actually write out the KL divergence, you're only left with the second term because the first term goes to 0. The second term is also called the cross entropy loss. And so the cross entropy loss is also simply called as simply minus log the probability of the correct class. We can revisit this. So one final term. It turns out that when we actually perform training, when we perform compute the neural network, we first compute these affine terms z. Then you put it through a softmax to get y's, and then you compute the divergence with respect to the y's. This term here is the derivative of the divergence with respect to the y's. But if you take it all the way back to the z's, it turns out that the derivative of the KL divergence with respect to z is simply going to be y minus d. You can prove, I can show this on Piazza, it's very trivial. And so it turns out that regardless of whether you're using the Euclidean distance, when you're trying to perform regression, we don't have any activation function. When you're trying to perform classification, we have a softmax activation. So in both cases, you get the z, the affine term z. And in both cases, the derivative of the Euclidean divergence, the L2 divergence with respect to z in the regression case, and the derivative of the KL divergence with respect to z in the classification case is simply going to be the error between the actual output of the activation and the desired output. That's very convenient. So we've defined all terms over here. I'll skip this poll, but actually, this is the end of the lecture. So I'm just going to give you this poll and we'll stop right here. Ten seconds. All right. I'll stop this. And can anybody tell me which one is true before I stop recording? Is this first statement true? Yes or no? No, right? The gradient may be 0, but it may also have a large magnitude, right? The rest of it doesn't make sense. And so here are the lessons for the day. Neural networks are trained to approximate function by adjusting their parameters to minimize the average divergence between the actual output and the desired output on training instances, and which are the input-output samples from the functions to be learned. And given also the loss to be minimized, to train them, several terms must be defined. The network, the manner in which inputs are represented as numbers, the manner in which outputs are represented by numbers, and the divergence function itself. So I will stop right here, but I'll continue recording. And if you have any questions, I can answer them. I suspect that some of you didn't quite get this, for instance, right? So does anybody want to have an explanation of what's going on here? Okay, so yeah. You have your desired output D, which is going to be something like 0, 0, 1, 0, 0, right? You have your actual output, which is going to be Y1, Y2, Y3, Y4, Y5, okay? This is how the KL divergence is defined. Okay, actually, let me see if I can go to the previous slide. So this is how the KL divergence is defined. D log D over Y, which is summation D log D minus summation D log Y. So let's take D log D, right? It's going to be D times log D, which is going to be minus infinity, 0, minus infinity. But then this minus infinity is being multiplied by 0. So this becomes 0 because log 0, increases much more slowly than 0. And this is multiplied by 0. So this becomes 0. So all of these guys become 0. Here, D is 1, but this is a 0. So this becomes a 0. So this first term always disappears, because it's either 0 log 0, in which case this 0 will dominate and kill it, or it's 1 log 1, and log 1 is 0, so this will dominate and kill it. In both cases, it becomes a 0. So this term disappears. That makes sense? Over here? Okay. So now let's look at the second term. It's going to be 0 log y1 plus 0 log y2 plus 0 log y3 plus 0 log y4, right? Because of the 0, these guys will disappear. Correct? Yes or no? So what remains? Just this one term. And so which is going to be minus of 1 times log of the probability assigned to the true class, which is minus log yc. That makes sense? Okay. So this is beautiful. Is this a function of this y? So let's say the target class is cat. So this is just minus log, the y cat, right? So will increasing the probability of dog change this? Let's say dog and camel swap probabilities. It will not, right? So the derivative is going to be 0 for the non-target classes, right? Yes or no? Okay. So you're only left with this term. What is the derivative of this guy with respect to the probability of the target class? That's simply going to be minus 1 over yc, correct? Yes or no? Okay. Now, what is this telling me? Is this derivative is negative, right? What is it telling me? Must I increase yc or decrease yc? Again, go back and remember this function, right? If the derivative is negative, should I increase it or y? I should increase yc, right? Y is always a positive number. So it's always telling me that I must increase YC. I must always increase YC, correct? This is good. So we got a sign check, yeah? Are you guys with me on this? Okay. What is the ideal value of YC? What's the ideal value of YC? It's going to be 1, right? The ideal probability for cat is 1, right? So when you have the ideal probability for cat, what is the slope? It's going to be -1/1. That's going to be -1, right? So in other words, when you actually arrive at the optimum answer, the slope of the divergence is actually -1, right? That makes sense? And so here's what we have. The KL divergence only depends on the probability of the target class. The way it works out, cross entropy loss is the same thing. It always pushes you to increase the probability assigned to the target class. But even when you get the maximum probability for the target class, the slope is not 0. Did all of that make sense?
Sir, one question. Increasing YC will reduce divergence, but it is -1 by YC, no? So increasing YC would reduce the
Okay, if the
negative
slope is
value.
negative over here, this is YC, this is divergence, right? So do you want the slope of the divergence with respect to, if I want to say increasing YC must decrease the divergence, right? So will the slope of the divergence with respect to YC be negative or positive?
Negative.
Exactly. You always want this sign to be negative when you want Y to increase, correct?
Right.
Right, okay. When YC is 0, what is going to happen? You tell me.
Divergence will become
The
infinity.
slope is going to be -infinity, correct? So it's going to be very steep this way. And it's going to tell me, come on, increase by a lot, increase by a lot. It's basically getting panicky about increasing by. Make sense? So, and so that's basically what we have over here. So even in the binary case is basically 2 classes. So this is, the 1 minus y is the other class. It's like having y1 and y2, only one of which is 1. So that's easy, right? But the whole thing makes sense. And so now when I spoke of this Euclidean case over here, once again, if this is D and this is Y, do you want to increase Y or decrease Y? If this is D and this is Y, do you want to increase Y or decrease Y? Decrease it, right? So what do you want the slope of the divergence with respect to Y to be? Do you want it to be positive or negative? You want to say that when Y increases, the error is increasing, correct? If Y is greater than D, then if Y increases, the error increases, right? Yes or no? That's what. So when Y is greater than D, this slope is positive. That makes sense? Because Y minus D will be positive. If this is D and this is Y, do you want to increase Y or decrease Y? So basically you want to say that increasing Y decreases the divergence, correct? Increasing Y decreases the divergence, right? So will the slope be positive or negative? Increasing Y decreases the divergence. Will the slope be positive or negative? Negative. Y is below D. This is going to be negative, right? Yes. And so this also satisfies. Just inspecting the sign of the derivative tells you whether you get, tells you what you must do for y to y in each case. And if the sign of the derivative is not giving you the correct information, then you have an error in the formula for a derivative. D minus y cannot be the derivative. Y minus d must be the derivative. You can see this directly by checking this, right? Okay, any other questions? Not. Stop.